All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park High School. Today is Friday, November the 22nd. It is the last day before Thanksgiving holiday. Woo-hoo! It is also a big day for Spain Park as we're traveling to Saraland to play in the third round of the state championship. It's been a long time since we've been there. Okay? It's also an... Huh? Well, we're not there yet. It's also an exciting day here in Advanced Level Chemistry as we're finishing up Chapter 5 about the periodic table. So Jonathan, if they're liking these videos, what should they be doing?
Hit that like, smash that subscribe button, and ring that bell.
And ring that bell. Here we go. All right. So, yesterday, we're going to get focused here. Yesterday, we talked about all the different classifications on the periodic table. Okay? So, the sections of the periodic table that have the S and the P, they are known as what name? Main group. Now add in here an alternate name. For some reason, there's always two names to everything here. Sometimes they're also called the representative elements. Representative elements. It's just a different name for the same thing. Okay? Representative elements. I forgot to tell you all that yesterday. For S and P. So what would be called the main group elements are also sometimes called the representative elements. Okay, so two different names for the same thing. It's kind of like your name and then your nickname. Okay? People call me Coach, they call me the GOAT. Okay? Alright. What do we call these right here? The D blocks. Transition metals. What about the F block? Rare earth or inner transition. So the name of group 1, minus hydrogen, the group 1? Alkali metals, and the word alkali means basic, opposite of an acid. So those are the substances that make strong bases. Group 2? Alkaline earth metals. The little known name of group 16? Chalcogens. 17 are the halogens. 18 noble gases. They're also known as rare gases or inert gases. And the word inert means don't bond, don't react. Okay, and you'll maybe notice if you ever read a label, sometimes you'll see inert ingredients. Things that are added but don't kill the bug. Things that are added but don't help anything. Okay? The inert ingredients.
I wear this shirt 3 times a week.
Yeah. Oh, you did work. I wore it today. I thought about it today. All right. So listen, there's a lot of energy in the room today. We got to focus it. That is what we learned yesterday. Today we're going to focus on what can we tell about it. And why are they called families? Why are columns called families? So what?
They've got similar traits.
Similar traits, similar chemical properties. Why do they have similar chemical properties? Look.
Because they have the same amount of valence electrons.
They have the same number of valence electrons. Somebody else tell me, what are valence electrons? Jonathan.
Electrons on the outermost energy level.
Electrons on the outermost energy level. So it's real important to know. All of these are P5. All of these are P4. 2P4, 3P4, 4P4, 5P4, 6P4. That's good. We already learned all that. Because they have the same number of valence electrons, the same outer shell electron configuration, that's what gives them similar chemical properties. Now, Mendeleev and Moseley, they didn't know all of that back then, but that's really why they're grouped together. Okay, so now let's look at, you have your blank periodic tables. We're going to do the atomic radius first. So find the one that says atomic radius. Okay, now notice down at the bottom, what does the definition say? Because you can't see it here. Somebody read the definition. Stella, read the definition right there for atomic radius.
The distance from the atomic nucleus to the outermost occupied orbital in an atom.
Okay? So we're going to talk about from the nucleus to where is that outermost electron. That's the atomic radius. Sometimes, and on the periodic table that I gave to you, they'll give it a covalent radius where they have that, and then it's the distance between the two nuclei, and then they just cut it in half. Because that outer edge, remember, is the electron held in a fixed orbit? No. It's in an orbital. It's just the most probable place. So the outer edge is sometimes a little fuzzy. It's a little bit hard to determine. So sometimes what they do is they just say, well, when atoms are bonded together, what's the distance between the two nuclei? And then they just cut that in half and say that this electron cloud ends there and the other electron cloud ends the other place. And that's how they get their covalent radius. So you sometimes have slightly different values on that. Now, this is pretty logical. What do you think happens as you move down in a family? As we go down this way, what happens? It gets bigger. Why? More energy levels. Okay? So you got 1 energy level, 2 energy levels, 3 energy levels, 4 energy levels, ladies. 5 energy levels all the way down to 7. So every time you add an energy level, it's getting bigger. Okay? So it gets bigger going down. Now, what about left to right?
If you go right, it gets smaller as you go right.
Smaller left to right. But why?
Like you said, it adds more protons, and the positive charge makes the negative electrons come further in.
Okay, so here's your nucleus. So you have your electrons. Well, let's just say on the second row. Okay, so here's your 2 electrons on the 1s2. But on the second energy level, you go and you start adding electrons. Well, I add lithium, I have 1 electron. I got 3 protons. And then I go to boron. I go to beryllium with 4 electrons. Did the electron add any more distance to it? No, because it's in the same energy level. But each electron is being pulled in independently of the other one. And so having 4 protons here now instead of 3, these electrons are both being pulled in more tightly. The magnet in the middle is getting stronger, so to speak. And then you go to boron with 5, so now we have 5 protons, so now they're all getting pulled in, so the electron cloud just gets pulled in a little bit more tightly every time. And I believe we left yesterday, as I was searching for the picture, and the picture looks like this. So you can definitely see the trend as you move down in a family, it gets bigger. And as you move left to right, it gets smaller. Okay? Now, we talked about valence electrons. When atoms form ions, when metals lose electrons, they get oxidized, they form ions, they lose their entire valence shell. So sodium, okay, we're going to talk about this, the oxidation state, the charge. All of these elements here, if they lose 1 electron, if lithium loses 1 electron, it's going to be the same electron configuration as helium. Sodium's got 1 electron out there in the 3s1. It loses that 1 electron readily and gets become isoelectronic, same electron configuration as neon. So metals lose electrons, they lose their valence shell to get that stable noble gas configuration. So if you'll notice there's a little 1 above the symbol, that means it's got a +1, that's the charge it tends to form. These all tend to form a +2. They're going to want to lose 2 electrons to become like a noble gas. The D's are all kind of weird, they do different things. But over here, these have 3 valence electrons. They're going to want to lose 3 electrons. Carbon, lose or gain, because it's kind of right in the middle, but tends to lose. It would be like a +4. But now when you get to nonmetals, it's easier for them to gain electrons to get to the noble gas than it is to lose. So if they gain 3, what charge would it get? it would have 8 electrons, but if nitrogen starts with 7 electrons, but it gains 3, now it's 10, what charge is it going to have? Negative what? I know, but it's negative, but how many? Negative 3, because it gained 3. Because it still only has 7 protons. It's an anion. Okay, remember we learned how to count electrons with anions and cations? Okay, so the anion, this is going to be a -3 anion, a -2, and a -1, because everything's trying to be like the noble gases. Okay, now here's a life lesson. We all strive to be like the rich folk. Okay? We all strive to gain and lose to try to become like the noble gases. However, they live an independent, solitary, they don't bond with anything. They live their lives as single monatomic atoms, never bonding with anything. Money cannot buy you love. Okay? So, we're all striving to think that this is going to get us happiness, but the reality is that we need to be content with where we are.
Talk to
But,
us.
but that's not the way atoms work. All atoms gain and lose. Atoms gain, lose, and share electrons to get to be like these noble gases, to get in this stable arrangement here. Okay? So when we look at the size of ions, what do you think is going to happen to the lithium atom after it loses that 2s energy level? Is it going to get bigger or smaller? Its radius is going to get smaller. Okay? So if I want to look and compare the sizes of ions, if we look at ionic sizes here, okay? Here's the lithium atom. Here's the lithium ion. Okay? Here's the sodium atom. Here's the sodium ion. Because when atoms form ions, they lose their entire valence shell, so they have one less energy level, so they're significantly smaller. Same number of protons pulling in, just one less, completely less energy level. Okay? Notice if we compare, let's see if I can go this way. If we compare, so here's magnesium. How many electrons is magnesium going to lose? 12. It's going to lose 2. It's got 2 valence electrons. It's going to lose both of them to become isoelectronic, same electron configuration as neon. Notice magnesium goes from here to significantly smaller. Okay? So cations are always significantly smaller than the neutral atom from which they came, because they're losing the entire valence shell. Does that make sense?
Yeah.
Okay? Now, so if we look at the whole trend, here, sodium loses 1, this is the sodium ion, magnesium has lost 2, 3, 4, notice carbon as a +4, it's just like a dot, okay? It's getting extremely tiny. Now, so you can see, but notice the trend is still the same. The trend is still getting smaller, because you still have more protons pulling that same number of electrons in, but they're losing more, it's getting smaller. Now, why do these all of a sudden get bigger? Say that again? Okay, because they're gaining electrons. So they're becoming anions instead. So instead of taking an energy level away, you're adding electrons to the same energy, and then those electrons are all repelling one another, so everything just kind of swells up. So nitrogen gains 3, so it's the biggest, gains 2, gains 1. So the trend still continues smaller left to right, but they all of a sudden get bigger. So anions are significantly larger than the neutral atoms from which they came. That might be worthy of writing down. Remember, you're taking notes on the back of the color sheet, or if you want to, write it on the ion sheet, that's fine. Whatever floats your boat. So cations are significantly, what? Smaller than the atom they came from. Anions are significantly larger. Cations are smaller, anions are larger. Cations are smaller than the atom they came from. Anions are larger. Cations are losing the valence shell. Anions are gaining to the valence shell. Metals get oxidized, non-metals get reduced. Leo goes Gur. Loss of electrons is oxidation, gain of electrons is reduction. All right? So there's our trends for both atoms and ions. Don't try and stifle his enthusiasm. We love the energy as long as it's focused and positive. All right, so that's the first trend. That's the first trend. Atoms get bigger going down because you're adding energy levels. They get smaller left to right because the electrons are going in the same energy level, but more protons, increased nuclear charge, pulls the electron cloud in more tightly. And then when we look at ions, they basically follow the same trend, but the cations are just much smaller because they lose their entire valence shell. Anions are larger because you're adding electrons in without adding protons, and so everything just swells up. And obviously the more electrons you add, the bigger it's going to get. This is 3, this is 2, this is 1. Okay? That's the first trend. Let's see, what do I want to do? Let's talk, since we already talked about this, let's go to oxidation state next. Oxidation state, I think it's actually on another page. Okay. So Kendall, real loudly read what the definition of oxidation state is. Y'all listen up.
The number of electrons that the atom needs to gain, lose, or share to get a stable electron configuration.
The number of atoms an atom tends to gain, lose, or share to get a stable electron configuration. What's the stable electron configuration? Say it again. 8, that noble gas configuration. Okay? We just talked about ions. They gain or lose electrons to get to have that 8 electrons, the noble gas configuration. When we get into bonding, as soon as we come back from Thanksgiving, we get into bonding, it's going to talk about how many electrons do they share. Okay? When it's a metal and a non-metal, what type of bond is it? Metal and a non-metal?
Ionic.
Ionic. What happens with electrons there? What's the key word? Electrons in an ionic bond. Come on, 8th grade, dig it up.
Say it again.
What happens to electrons with a metal and a non-metal bond? Okay, well, hold on. You just always talk without thinking. Okay? Okay, hey, I'm just saying. You're looking it up. That's why you cheat. You're looking it up. No, put that away. Put that away. Put that away. Okay? Now look. First off, let's think through this. Put it up. It's an ionic bond. What do you think things that have an ionic bond are composed of?
Charged ions.
Ions, right? That's kind of redundant. Charged ions. Ions by definition are charged. Okay? Ions, okay? Look. So how do we make ions?
Like charging.
By gaining or losing electrons. Listen, this is deep. In an ionic bond, then, electrons are transferred.
Oh my God.
Okay? Metals lose, making,
Non-metals gain.
what charge do they make if the metals lose? Cations. Non-metals gain, anions. Positive, negative stick to one another. You have an ionic bond. Yes, sir.
So it basically like steals an electron.
That's right.
So you gotta keep an eye on it.
Oh my god.
For an ionic bond, you're keeping an eye on. I'm trying to follow the joke there, but okay. An ionic bond, you got to keep an eye on it because it's going to steal. Now look, but it's not really stealing because the metals gladly give up their electrons because they want the noble gas configuration. The nonmetals gain the electrons. It's a mutually symbiotic relationship. They're both happy. So positive to negative, then they attract. In covalent bonding, they just share to get to the 8. And we're going to talk about that. That's when we do those Lewis dot structures and we see how they share. Okay? Yes, ma'am. Okay, I asked at the beginning of class over and over again, who needs the sheets? Okay? You have this one? Okay, what happened is I gave y'all two. Does it not have it? Okay. Now look. Okay. So we gain or lose. So the oxidation state tells me how many electrons an atom tends to gain, lose, or share to get to that noble gas configuration. We've already talked about it. Group 1. Okay? Group 1. How many electrons do they need to gain, lose, or share to get to be a noble gas? Okay? Needs to lose 1. Group 1. These all have 1 valence electrons, right? This is 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. If they lose 1, they get the noble gas. Now again, if I did the noble gas configuration for lithium, wouldn't it be helium and then 2s1?
Yeah.
That's my noble gas configuration, right? So it's going to want to lose this 1, then it has the noble gas configuration. Neon, 3s1. Loses 1, it has the noble gas configuration. So these are all going to have a +1 oxidation state. They're going to tend to lose 1 electron when forming a bond. So what's group 2 going to be? +2. Okay? Now we're going to skip over all the D's. They have a whole bunch of different ones because they can't really, there's so many they would have to gain or lose. They do different things. We'll talk about that next unit. Okay? But over here in group 13, how many? So this is 2s1, 2s2, 2p1. So how many electrons are they going to need to lose? Houston? 3. So what's the charge oxidation state going to be? +3. Now carbon, 2s2, 2p2. Okay? They're kind of right in the middle. They can go either way. So they can be plus or -4, but it's almost always +4. And carbon generally doesn't lose 4 electrons. It's going to be more about sharing in covalent bonding. Okay? So what about the nitrogen family? -3. This is going to be -2, -1. And then the noble gases, they don't bond with anything, so they don't have an oxidation state. Okay? If it ain't broke, don't fix it. Okay? So there's your oxidation states. That's going to be huge for us in bonding. Next unit. But it's pretty easy. +1, +2, +3, plus or -4, -3, -2, -1. 1, 2, 3, 4, 3, 2, 1. Okay, it's all about getting the noble gas configuration. All right. Now, that was quick. Let's talk about this thing called electronegativity. All right, and I'm gonna take it all. I did. But I'll let you read this.
It's Jackson. Somebody where is he?
Yeah, I saw it.
So we're going, and then we bring our own lunch, and then we stop for walkthroughs for football, and then we're going to walk through this where
I can't see.
Alright.
Oh yes.
Go ahead, look at, read it. What is this thing, electronegativity? Okay, y'all listen up, refocus. Here we go. Lucas, read it loud.
Alright. The distance from. No, that's the wrong one. The ability of an atom to attract a bonded pair of electrons from another atom.
The ability of an atom to do what?
To attract.
To attract, okay? It's an atom's attraction for a shared pair of electrons. What is a shared pair of electrons? What type of bond is that going to be?
Covalent.
In a covalent bond, okay? So if I'm looking at, you guys maybe all did your Lewis dot structures for like oxygen. Oxygen has 6 valence electrons. So each dot represents an electron. Do you remember that from 8th grade?
Yeah.
Okay? Oxygen has 6 valence electrons. Hydrogen has how many valence electrons?
1.
1. Okay? Now I'm going to draw an X for hydrogen, but all electrons are the same. Okay? All electrons are the same, so it doesn't really matter, but I'm just trying to show the source of the electron. So the hydrogen's going to come in and can bond there, and another hydrogen can come in and bond here. So now each hydrogen has 2 electrons, because it's sharing, so it's like helium. Oxygen now has its 8, so it's got a stable configuration. So they've shared and made H2O. Okay? But in the bond, it's a sharing. But if you know in life, sometimes when you share things, it's not always an even sharing. Sometimes some people hog what you're sharing more than others. If you happen to have to share a car with an older brother or sister, they get to drive it a whole lot more than you. Okay? If you had to share a gaming system, if you're the older brother or sister, the younger one just gets it when you don't want it. Okay? Even though you're quote sharing it. So there's an attraction for this shared pair. There's a nucleus here, and there's a nucleus here, and the electrons it's a tug of war for the electrons. The electronegativity is that tug of war for the electrons. It's a scale from 0 to 4, with 0 being weak and 4 being strong. Okay? When we look at this, francium, is this hydrogen, lithium, sodium, potassium, lithium, so this is francium. Francium has the lowest, fluorine has the highest. This is, most books that call fluorine 4.0, the highest on the scale. Your periodic table gives it as 3.98, a little bit more accurate. Come on, Steve, you can write. 3.98. Francium is 0.7. The alkali metals as a whole have the lowest electronegativities. But just looking at this, what do you think the trend is?
From left to right. Or from.
Okay, so as you go down, what do you think happens to it?
Gets weaker.
Okay, if that one is my biggest one and this one is my lowest one, as you go down, the atoms are getting bigger, but the attraction for the shared pair, that shared pair is going to be farther away from the nucleus, so it's going to get weaker, it's going to be lower, and it's going to get higher right to left. Pardon me, left to right. So the trend is this. Okay, that's where it gets bigger. Now look, so if you combine a metal, low electronegativity, with a non-metal, high electronegativity, what does that mean about the sharing of that electron? If you have a low, super low, and a super strong.
The super strong is going to get more use out of it.
As a matter of fact, what type of bond forms when you have a metal with a non-metal? Ionic. So is it really a sharing? No, that just takes it. So in other words, it's such an uneven sharing, it's really just a transfer. On the other hand, when you start getting to non-metals, now their electronegativities are a lot closer to one another. They have about the same pull. One's not able to pull the other one away completely, so hey, let's share. And so if you look at the periodic table that I gave to you, your color periodic table, you got one right? No, not that one, the actual color one. The real one. Yeah, that one, but here we go. If you look at this one, look on the back of it. If you look on the back of it right here, you can go even bigger. If you look at the back, we have our difference in electronegativities between the two atoms that are bonding. Okay? Now, those values are all given on that periodic table, but if you look at the differences, once the difference gets between 1.7, now it's more 51% ionic. It's more ionic in nature than it is covalent, so we would call it an ionic bond. When it's less than 1.6, the difference between the two, how much is hydrogen pulling versus this one? Okay? Then it's going to be more of a covalent. We're going to learn it. We're going to call this thing a polar covalent bond, where it's an uneven sharing, but it's not a complete transfer. Okay? So we can look at this electronegativity. So this is going to be real important again when we get to bonding, just knowing the trend. But it's really easy. Bottom left is the lowest, top right is the highest. Why don't we include the noble gases? They don't bond. They don't have attraction for a shared pair of electrons. They don't attract anything. Okay, so we got one more trend. Last trend. Oh, good. Does it still hurt?
Yeah.
All right, here we go. All right, lots of energy still. We got 10 minutes, 15 minutes to get this last trend. Yeah, 15 minutes before most of y'all are done with school for a week.
That's not fair.
All right. Okay, look. Ionization energy. Okay? So, who wants to read? Go ahead, John.
The energy needed to remove an electron from a neutral gaseous atom.
Okay? So, too many people were talking when he did that, including.
Oh my.
So, Lucas, you want to talk? So, read it again. Read it again.
The energy needed to remove an electron from the neutral gaseous atom.
You finally have a chance to talk and you mumble it out. Okay? Come on, man. I'm trying to help you out. Come on. All right. The energy needed to remove an electron from a neutral gaseous atom. So in other words, how much does it take to remove an electron? Now, why is that important? Well, what does it mean about the stability of Aaron? Focus. Okay, come on. What does it mean about the stability of the electron configuration if it takes a ton of energy to remove it?
It means it's very strong.
It means it's strong. It means it's stable. It takes a lot of energy to remove it. If it comes off easily, that means it really doesn't care. It doesn't really want that electron. So the ionization energy gives us insight into which electron configurations are the most stable. Now, what do you think? as you move down in a family, what happens to the size of the atom?
It's larger.
It gets larger. So as the electron gets farther and farther away from the nucleus, you think it's more or less tightly held? Less tightly held. So what do you think that means in terms of its attraction to the nucleus? It's less tightly held. So what does that mean about the ability to remove it? It takes a lot of energy or less energy? Less energy. So the ionization energy decreases going down. Now as we go left to right, in a period, what happens to the size of the atom? So what does that mean about the electron cloud? It's getting held more tightly every time, right? So it's stronger. Okay, so the ionization energy increases left to right. Okay? So as it gets bigger going down, as the atoms get bigger going down, it's easier to remove the electrons, so the ionization energy decreases. As you go left to right, the atoms get smaller, the electrons are more tightly held. Now we want to look at one other trend in that if you remove successive electrons. Chapter 7. Okay. Golly, you guys are highly energetic today. All right, come on. Hey, ladies, here we go. I need last few minutes. Come on, 10 minutes. Back row. Come on, focus. Here we go. Here we go. If I want to remove successive electrons, not just the first electron, but I want to remove a second, a third. Sodium has 11 electrons. How much energy does it take to remove the first one, the second one, the third one, the fourth one, the fifth one, all the way up to 11? Okay? Notice with sodium, the first one is 496. Notice the general trend going down. Okay? Well, actually, pardon me. Okay? This is going across in a period. This is going from left to right. So what's happening to the atom? It's getting smaller. So what's that mean about the attraction for the electron? Getting bigger. And so notice that the ionization energy is increasing as you go across the period. Now there are a couple of irregularities that unfortunately I don't have time to get into. They're really cool, but take AP Chemistry and we'll talk about them. Okay? But now look, after sodium, okay, which is going to be 3s1, okay, a noble gas that's going to be neon, 3s1. After it loses one electron, now notice huge jump in ionization energy. Because the first electron's on the third energy level. Where's the second electron going to have to come from? From 2p. Closer to the nucleus, much more tightly held, noble gas configuration. Very stable, so there's a huge increase in ionization energy. Okay? Now, magnesium is going to be out here at 3s2. It's going to have 2 electrons out here in 3s. It's going to have 1s, 2s, 2p. Those are all going to be filled, but you have 3s2. Now, it's smaller than sodium. So there's an increase in ionization energy. Okay? So you take the first one away. Now you're trying to take something positive, something negative away from something that's positive. Plus, there's no electron-electron repulsions going on anymore. This electron, even though they're opposite spin, they're still repelling. And so this electron could really say, hey, can I help you pack? It's okay, you can leave. I'd like to have this space to myself. So the difference here is really the difference in lack of electron-electron repulsions. But the second one still comes out relatively easily because it's still up here on this third energy level. But then, Where's the third one have to come out of? 2p, much closer to the nucleus, more tightly held, noble gas configuration. So again, we have this huge jump in ionization energy. That's telling us something, that there's extra special stability about that noble gas, that filled octet, that 8 that you learned about in 8th grade. The ionization energy kind of tells us that. So aluminum now has 3p, it's got 1 electron out here. Well, now that 1 electron's a little bit farther away than the S's, and so there's actually a slight decrease in ionization energy. It's actually a little bit easier because we started a new sublevel. But then the second one then comes out of the S. Our third one still comes out of the S. And then there's the big jump once you've lost that valence shell. Once it becomes, and that's why aluminum will form a +3 ion, but it's not going to form +4. It takes way more energy to get that fourth one out. The first 3 come out relatively easily because they want to get that noble gas configuration. So there's always a big jump once an atom loses enough electrons to get that noble gas configuration. That tells us, hey, there's something stable then about that filled octet. That's what everything tends to want to get to. So this goes hand in hand with our oxidation state. Sodium forms a +1 because it loses 1 easily, but it's not going to lose the second one. Magnesium can lose 2 relatively easily, losing that valence shell, but then once it has that noble gas configuration, it's not going to want to, it takes way too much energy to lose the third one. It's not going to do it. Okay, so that tells us why we have those oxidation states for those metals like we do. The ionization energy gives us all of that. Okay? So we should just be able to know the basic outline of the periodic table, as well as the names of the families, and now these 4 trends of atomic size, and along with ions, oxidation states, +1, +2, +3, the charge, the number of electrons they tend to lose, gain, or share when forming an ion. We should be able to know about electronegativity because that's going to be an attraction for electrons. That's going to be huge in the next unit. Just biggest thing is francium's the lowest, fluorine's the highest. And then this thing called ionization energy, which is really dependent upon the size. The bigger it is, the easier it is to remove the electrons. And then once it gets the noble gas, it's stable. All right, so you have one assignment for Thanksgiving. Okay? Well, that's gonna be an easy thing to do. I was gonna tell you sleep in and get rest, but you do that naturally. I don't have to assign that. Okay? But you need to make sure that you take time to tell the people around you, your parents, your grandparents, your friends. Tell them how much you appreciate them. Do something special for them. Okay? Have a thankful heart. Okay? This is the people in your circle. Tell them how much you care. And y'all, all of you around the world watching these videos, y'all have a great day, a happy Thanksgiving, and go Jags.
All around the world.